I'll try to give an overview of actually just some thoughts about agentic AutoML systems. The book on this has not yet been written. It's the very early days. People are just experimenting with different tools. We have a few nice ones that we can discuss. But I also want to focus a bit on the relationship between agentic AI and AutoML and how it changed our perspective about what AutoML may mean in the future. This is also why I titled it Towards Automated Data Science. Right? Can we not just do hyperparameter tuning or tuning models, but can we actually automate data science more generally using agentic AI? And from there, it's also a small step to automating science in general. Cool. Now, so imagine you have some data and you want to build an advanced machine learning model. You can do different things. One thing you can do is you can give it to your fast-talking, fast-typing intern, which is your LM, and he will just code up some Python code in 30 seconds that builds this entire complex model for you. Downside, he might actually delete your entire server in the meantime because it's not paying a lot of attention to what he's doing. It's not doing a lot of testing. So it has also downsides, this approach. The other thing you can do is to use your trusted model building tool, like the AutoGluon or your AutoML tool, your AutoScikit-learn, which is very good at performing systematic hyperparameter tuning, pipeline building, and so on. But it's restricted to this pre-formatted search space that somebody defined, which is oftentimes like an idealized version, which is not a jab. It's just like if you want to build like an optimization framework or process, you need to somehow define what the variables are, what the buttons are, right? So that's sort of intrinsic to this way of solving the problem. But this also ignores the messy reality of data science. Oftentimes, there are variables you have not thought about. There are some weird things in the data. Some data is entirely lacking. Maybe the question is wrong. Right? So those things are much harder to include into a traditional AutoML pipeline. So LM code generation. This is our fast-talking intern. Nice things are you can ask any question in plain English. Right? It's very flexible. You can basically ask anything you want. Doesn't mean it's already solved all the time, but if with some experience you can be very flexible in the questions you ask. And it's great for democratization. You don't need to know how to code. Anybody can do this. Also nice is it covers everything from the very messy data cleaning, even things you did not think about. It knows the semantics of the data, so it can look for additional data you may need, all the way to model building and deployment. So it covers a whole larger section of the data science pipeline. And it really understands the semantics of the data. It knows what a column name means and can use that to make informed decisions. If needed, it can fix issues. It can import more data. All the different things that it can do because it has these kind of tools. It can talk to the internet. It can look up things. It can include this, just like a real data scientist would. Problems, one of them is single pass conversions, right? So these tools, they spit out a lot of Python code. Typically no iteration, like the latest models, they have iterative self-improvement, so they're a little bit better in this respect. But most LLM tools don't have that. They don't really try different data cleaning techniques. They just find something that works, and if it passes all the tests, they're happy. It doesn't mean they have the best solution. It's just something that works. Answers the question. And oftentimes there's no in-depth testing defined. Second, and oftentimes I think a longer term problem is context explosion. While these agents are doing this, so they try, they write code, they test it, they rewrite, they get errors, they fix the errors. And while they're doing that, they build up this huge log of outputs. They do previews of the data, they have code snippets, they have error tracks, stack changes. And all of this builds up in the memory. It has to have all of this in its context, right? And this context is limited. It can only have so many tokens of information in the context. And the more data is in the context, the harder it becomes for this tool to work well, right? And especially if you do agentic and you add more tools, more capabilities, this makes it even worse. Right? And what you get there are things like the lost in the middle phenomenon. Who has heard of this before? Yes, a few people? Right? So it means that as your context grows, the stuff that's in the middle sort of gets ignored. And this is related to how attention mechanisms work. And because all important, very important details may get buried in this whole process, reasoning may fail. And you may have noticed it before. You're working on a piece of code. Claude is doing a great job. I'm helping you, but at some point, it's just somehow not getting what you want. It just forgets something you discussed 2 minutes ago. Or you can say, oh, can you update this function? Which function? I just write a new one, right? So it loses this information. This is still a very important problem. And also sort of related is this obscured credit assignment. Because the context is so oversaturated, knowing what's the cause of a bug or successful output becomes very hard to track for those agents. Right? And then it's generally out of token errors. Sometimes, at some point, it just hits the limits it was designed for, and it just doesn't work anymore. Right? So all these things should make you very skeptical about just always going to this LLM tool to fix all your problems. So, but can we get something in the middle? Something that's the best of both worlds, right? So it should do flexible problem solving, but should also be able to use systematic techniques to build the best models, best pipelines, best data cleaning, and so on, in the right context and in the right roles, right? Is this agent helping you as maybe like just a coding partner, or is it actually giving advice? Those things also have to be very well defined. Any questions so far? Okay, so agentic AI, lots of, I'm not often on social media, but every time I'm there, it's full of agentic AI. And it's going from super hyped, nice things like, okay, hospitals are using it to save patients, to all the way to, a startup has deleted all its data and now it's bankrupt, right? To also very funny things where the AI is just not making any reasonable predictions and leads to very silly things. Okay, you had a tutorial on agents already on Tuesday. It's a very small refresher, right? So an agent, let's have some definitions, is basically an intelligent system that interacts with the environment. So what does intelligent mean to you? Any thoughts?
For me, intelligent would mean that it's capable to follow my instructions up until a point that can have a verified result or something, and it's like autonomous and makes a good effort at that, not something that's, I don't know, then I look at it later and it's like...
Okay, good, very good, yes?
I think something that can autonomously identify what it's working with. In a sense, if you ask it a question, it should know the inherent rules that it needs to answer that question.
Okay.
Like if you ask it to calculate how long a ball will take to fall, it should figure out it needs gravity and then it needs to know the value of the gravity. Stuff like that, which you shouldn't have to explicitly mention.
Exactly. So it should natively understand what you're doing.
Yes.
It should be able to follow instructions. Anything else? Yeah?
You just say different problem solving. So that means as you described, like some kind of almost active inference. Obviously that's the content-rich association-rich, but like I think it calls like independent sampling and then problem solving. So getting a problem and then solving the problem is kind of the sense as the system.
Yeah. General problem solving and learning here as well. Yeah.
I view it as a property of any system that system which can make predictions without being explicitly designed to make these predictions.
Okay, so to generalize, right? To make prediction that does not train on. Yes. Okay. Good. So all these things are very important to build AI agents, right? So they should know about cause and effect, right? Be able to generalize, understand the world, and be able to interact with it, and learning, right? So to remember and to improve from experience, right? This is true for agents in general. whether it's an LLM agent or any other agent like a robot or anything else. Agent frameworks typically are not one piece of code, they have different parts. One thing is a way for the user to talk to the agent, right? So the user can communicate what the problem task is. Typically, with LLMs, this is a prompt, like a text question, but doesn't have to be, right? It could also be anything else for the user to interact with the agent. Agent is the central reasoner, the coordinator, the brain of the system. It typically has some kind of planning ability, right? So it can take a question, understand the question, and break it down into smaller chunks that they can be handled independently. It needs to have memory, right? So it has to memorize what it learned before. It needs to memorize what did I do before, did I work or not? It needs to be able to observe. It needs to store all this in memory. And typically, most agents have two kinds of memory. They have a short-term memory, which is the context window, which is basically your working memory. It's what I have in mind right now. And long-term memory, which is not in the context initially, but can be retrieved, right? So in response to certain questions, it can decide, oh, I need more information. I'm going to do a lookup. I'm going to put more information. I'm going to, maybe there's a RAG, like a retrieval augmented generation. There's a database I'm going to consult to get more documents in. So they have those two things. That's very important to know. There's a short-term memory, the context, and long-term they can access other information stored somewhere else. And it has tools, ways for the agent to interact with the environment. If it's a robot, it means like it's the wheels, it's moving. If it's an LLM, maybe it's a coding tool or code execution tool, or a web search and so on, right? Okay. It needs to have cognition, it needs to know how to reason and plan. Those things are very important. And so when you choose an agent, you should check that it can do that. It should have perception, it should understand the environment, right? And nowadays, an LLM is sort of limited in that sense. It only sees the text or your desktop or whatever it's working in the environment it is. But this is not generally a problem. If you think about a constraint, so if you think about AutoML right now, it's basically inside your computer, but maybe you have an AutoML system that learns inside a robot, right? And then the robot has cameras, it has to also observe what's happening, it has to see what's the effect of my actions. If I move, will I fall over or not, right? That's also important. And ways to interact with the user and the environment. Okay, now what's an sorry, yes?
So in the previous slide, the planning, it's something that an LLM may do or may not do. It's not something inherent that always exists.
It's something an agent may or may not do. Yes, so for LLMs, typically they do that. If it's another kind of agent, maybe not. That's true.
Like if you use a small model that may not have thinking capability, then the planning may not exist.
Yeah, but then the question is also like, would you call that an independent agent? If it cannot plan ahead or plan how to answer a question.
So I mean, there's no protocol or there's no framework that says the planning should be in a certain way that is independent of.
No. Yeah, so the planning does not have to be like a separate module. It can be like an intrinsic ability of other things it's using. That's true. Yeah. Sure. Okay. Now, what's an LLM agent? To be more specific, it's basically an agent with an LLM backbone, right? So not all agents have to have an LLM backbone, but for this talk, we will assume mostly that we're dealing with LLMs, which means it has a backbone LLM. It's some model it's built on. It cannot be any LLM. It has to be one that's fine-tuned for tool use, right? So if you just have like a pre-trained model, it won't do anything. You need to learn it how to follow instructions. You need to teach it how to use tools. A lot of models nowadays have been pre-trained for doing that. That's not always a given. And not all models are equally good at that, right? There's a nice leaderboard. See this works. Okay, so this is the Agentic leaderboard. So here you can see like which models are good at tool use, right? So for instance, Claude is very good at it. There's Gemini, GLM, O3, Kimi. So these are the ones which actually are very good at tool following, instruction following or tool use, while others like, I think, Llama and so on are not very good at that. They're actually pretty bad at that. So it's good if you are going to choose which LM you're going to use for your agent, take into account what they need to do. And as we'll see, you oftentimes will have not one agent, but a set of agents working together. And you may have one agent which is more like the orchestrator, and you have other agents which are more the executors, the workforce. And basically the working agents, they need to use tools. They need to be very good at that. While the orchestrator maybe needs to be better at reasoning or planning. So in principle, you can use different LMs for different agents, if you want to. It's not always a good idea. Any idea why? Yep. It has been observed in different papers that different agents, different models, oftentimes don't agree with each other. Right? So you can ask the same question to Gemini or Claude or something else, and they may fundamentally disagree on the answer. They might be slightly different or very different in meaning, which means that if you build like an agentic system with different types of models, it may start conflicting. Right? So for that reason, there's a bit of a debate on how you want to do this. Either you use the same LM for all your agents, or you can use different ones, but you have to have a good reason to try different ones because it can also cause some dissonance in the interaction between the agents. Okay. Yeah?
But can that, I don't know, can that not also be seen, for example, like also a way to ensemble different LLMs? So for example, I see that ChatGPT is sometimes making the same mistakes over and over. It's just missing, I don't know, some capabilities there. But for example, if I would let it debate with a Claude model perhaps on how to plan something, it might be made aware of its mistakes, right? Like in a way, the whole ensemble members have like weak stuff, and then the variance reduces if you ensemble. Right?
That's true. Yeah. So you can have different agents talking to each other to come to a consensus, and hopefully that consensus is better than the individual one. Yes. I think in general, yes. If your agents are capable enough to come to a consensus, they probably will. It's the same with two humans. It's like it's hit and miss. So the two humans might agree at the end after they talk to each other, or they might fundamentally disagree even more. So yeah, overall, I think it's a good idea. It's a bit more expensive, but you can do it. Yeah. All right. It also needs actions. And we call those tools. So tools you saw this on Tuesday as well, right? So tools are different things, basically functions that an agent can execute to get more data, to do some actions. And it needs a system prompt instructions that we give beforehand, either in the form of a system prompt, like you say it like, oh, you are an expert AutoML scientist, optimizer. So you have to give some context. And these days we also have these skill files which specify specific skills. I'll get back to that. Okay, quick quiz. So which are LLM agents? So an LLM system that browses the web. Is that an agent? If yes, raise your hand. Only one person thinks it's an agent? Why do you think it's an agent?
Okay, so it's definitely taking some actions, right? The environment would be the internet. It has to look up for some search terms and get back observations. Yeah, that seems pretty agentic.
Yeah. So if it browses the web, it accesses information it was not trained on, right? And so whenever an agent has to get external resources, it's basically using a tool to do that. Right? Yeah. So that's definitely an agent, an LM agent. GPT-4o with complex reasoning, is that an agent? Nobody raised their hand? No. That's correct. So it's not an agent because it does it internally. It doesn't need to call anything externally. It doesn't need to interact with the world at all. An LLM that takes in a question, plans a solution, and then applies changes to a code repository. Yes? Yes? Most people yes, because it needs to execute code. It can't do it by itself. It needs to have a code environment. Second one, very similar. A coding agent that identifies a bug, creates a branch, writes code. Even more so, it needs to, of course, do that. An LLM that takes English text and outputs French. Nobody? No, it can do this natively, doesn't need tools, okay. And an LLM that fine-tunes the high parameters of a machine learning model, machine learning algorithm. Not convinced? Yes? Why yes?
Because, I mean, fine-tune hacker parameters and change them in a different data set, like you need access to the data set, you need access to the algorithm, and actually have an environment to run it, like analyze how to change it.
Exactly, yeah. So anyway, how it does it, it may like call like a basic optimization tool, and of course it has to call this tool. This is not native to its knowledge, right? Even if it writes code, it needs to execute the code to do the optimization. If it like say it just re-implements random search, whatever, it needs to execute it, right? So it definitely needs tools, right? So for anything AutoML-like, you will need agents. Right. Cool. So what is a tool? A tool is basically, so now we're going to go a little bit deeper. So a tool is basically just an external function or an API that allows an LLM to interact with the environment. It's always external to the LLM, and typically it's a piece of Python code that's executed. And it has a very specifically defined function interface with input and output parameters. Right? So you need to tell the LLM what the name of the tool is. You need to say what it does. You need to say these are my inputs and this is the output you can expect. And you need to somehow tell this to the agent. When do you need tools? Whenever you need to have something that it can't answer without the tool, like knowing the latest information, it doesn't have this in its training data, so it has to look it up. Doing some complex math, it needs, of course, to call like some math tools. Look at the weather, it doesn't know this, it has to look this up, right? For these things, you need tools. So the typical way, well, there's different ways you can do tool calling. The simplest way is just to the client. The client is your cloud desktop, it's your web interface where Gemini is running or GPT is running, wherever you're talking to the agent, it's your client. You're going to the client, you're going to send a question. For instance, what's the temperature now in Milan? And you're not just going to give the question, you're also going to tell it that there is a tool, Get Weather, that can answer this question. Right? And so typically a client has a number of these tools and basically tells the LM agent, here's my question, and here's a list of tools you can use to answer those questions, right? In this case, it's only one, but it can be a whole list of different tools. Okay, so the LM sees this and says, well, I don't know what the temperature in Milan is, but hey, I have this tool, Get Weather, I can just call it, right? So it does this, it calls a tool, it fills in information, okay, Get Weather, and the user was asking about Milan and Italy, so I'll just add this information. The client gets this, executes this, for instance, calls a weather API, gets the result, sends this to the LLM, and then only the LLM answers, well, the current temperature is 30 degrees. Very simple example. So here, all the tools are known by the client. This is not very scalable because then the agent, well, the client, I mean your code desktop or your Gemini interface needs to know all the tools in the world, also AutoML tools. It can't do this, right? So for this reason, we have things like MCP to solve this. I can send you the collab for this. So this is like a full implementation of a tool calling example. So we have some function, get current weather, it only needs location, and it returns a string. And we also describe what it does. So location is the city and the country, so we define what it needs. And it returns a sentence describing the weather and location. That's the tool. To explain the tool to the LLM, we need to have a function schema. This is a piece of JSON. It says, well, this is a function. The name is current weather. It has parameters like location. This is a string, and so on. And this location is required. So this agents which are trained to do tool use, they understand this. They can parse this Python code, this JSON code, and then know how to call the tools correctly. If this was an AutoML tool, you would, for instance, have your function could be like run autoscikit-learn, and in the parameters you would give the inputs that it needs, like the data set, maybe it's a budget, and so on. So you need to define all the things that the AutoML tool needs, and what the answer would be. Maybe it's one number, or a string of parameters, or pipeline, and so on. So you have to define this to the element. Okay, this is just the code around it. On the left here, we start just a local client, which is Llama. The prompt is some system prompt, like, okay, you are a helpful assistant. When users ask about the weather, use this function to answer it. And then the next question I'm going to ask. And then here, I call the client, and I say, well, use this model. This are your prompts. These are the list of your tools. And you can choose which one automatically. That's the whole code, and now I can ask any questions, and we'll get the answer. It's super simple to implement. Any questions here? Yeah.
I'm wondering. I also saw code bases about for the agentic systems, which really blew up so fast in complexity. If you don't have a standardized way to do that, it's really hard. And I mean, okay, there's something like line graph, which is like a really low abstract, high abstract. Are you aware of any more unified, like a torch for agentic systems, perhaps, that would unify it a bit more?
Like other than MCP, or? Like,
I mean,
the simply MCP is like sort of right now. This is a standard, like how you would define those tools. Yeah, we'll dive into this right now. Any other questions? Yeah? Okay, cool. All right. So basically, if you want to build an AutoML agentic tool, all you need to do is to write some functions that do AutoML stuff. Just explain them to the LLM, and you can start. You have your agentic LLM. Your agentic AutoML tool. Okay, cool. Model context protocol was briefly mentioned Tuesday as well. I'm just going to short reminder here. Why this exists is because, say you have 100 tools and you have 100 models, you don't want to like implement this function for all the different kinds of tools. So you don't want like n times m maintenance of all those things. So MCP is like an open standard for explaining stuff like this here. For connecting AI models to any external data tools. Right? It has kind of a client-server architecture, so it has a host, which is where the AI model is running. Again, that's your IDE, your cloud desktop, and so on. It has a client, which manages the connection to the MCP servers. So servers are the ones that provide information. So maybe it's GitHub, has an MCP server to, for instance, take pull requests. Maybe it's Slack that has an automated message, or a database which has an MCP server to get data and return it to you. Right? The client manages this connection and basically gets the data and then sends it back to, there's no mouse here. So, okay, so you have a question, send it to client. The client then does the calling. So, okay, I need to call this guy. It has a URL. With the URL, it calls a server somewhere with some commands, API. It gets data back, and then this then gets the results, strips all the not important information, and sends it back to the LM itself. Yep. And that's basically it, right? So, and when you want to use MCP, it's quite simple. You have tools like fast MCP, which makes it very easy for you. Yeah. So this is, for instance, how it looks like in fast MCP. This is decorator. Oh, this is one tool. It's a function. This is email draft writer, the recipient, structured body, and so on. And then this function will write an email and then send it back. And basically, this little decorator does all the complexity behind it. Right? So that makes it very simple. You don't need to set up your own client and server and so on. You just need to write your function, add this decorator, and then you can run your own MCP server. Right? And then you just have to tell your LM, oh, my server is here. You can talk to it to use these tools. Yeah, and so the same way you can expose any AutoML tools. Yeah, and you can combine with other tools. You can, and this is very powerful, right? So you can use your AutoML tools as you are used to them, but you can also expand it with data lookup, data cleaning, other things. And LM agent can then neatly intertwine data lookups and cleaning with traditional AutoML systems. Okay. There's a little bit of, I think, yeah, explosion in the types of ways that we can build agents. So nowadays, we talk about tools, skills, and agent files. So the tools are, like I said, that's your code. That's just a JSON string that explains to the LM what the tool does. It's basically a description of an executable function and uses MCP to describe this. Now, that's only the tools. It doesn't have any knowledge about when or how to use those tools. This is typically described in a skills file. So a skills file gives instructions. So it tells you, oh, if you get a question about X, you should use tool Y to answer this question. And if you use tool Y, if you use this tool, say the tool has something like fetch a data set, the skills could say, oh, well, first check how big this data set is. If it's like a 5 terabyte data set, don't just download it. Maybe try to get a small view of it, right? So in the skill files, you can basically express all your data science information, your knowledge about what makes the system work well. Oftentimes, these things grow organically. So you start with an agent without any skills and does something horribly wrong, and then you adjust the skill files to make sure it doesn't happen again. Right? And so in the skill files is just like it's an MD file where you can add like a whole list of instructions on how to use those tools, and whenever you then the agent decides to, oh, maybe I should use this tool, it will look up how do I use. It will read the skill file that gets loaded into the context, then reads this, and then knows, well, can use those tools more effectively. There's also these days an agents file which describes the different identities or roles of an agent. Right? So more generally, like, okay, you are a data scientist. How does a data scientist work? A data scientist starts with first looking at the question, seeing what data I need to answer this question. Then it's going to build some experience, it's going to visualize the data, it's going to talk to other people. Then you're describing this persona, basically, is often done in an agents file. Also says what the constraints are. You can say something, oh, if a process takes more than an hour, just kill it, don't keep running. Or other constraints you want to define. Also constraints like you are allowed to execute code or not, or you're allowed to execute some kind of code and some other code not. Yeah, so this dictates which skills and tools the agent is allowed to process. And so this gets loaded typically by the MCP server automatically. And the clever thing here is that you could basically just put all this information into your system prompt that you give whenever you start, but this will lead to an explosion of context again. Right? If you have 50 tools, you have this whole description in your context before you even start asking a question. Right? So this is going to add to your context explosion. So for that reason, this is a nicer way because the LM will only include those skills if it is thinking about using a tool, yes or no.
And so you are dividing it into tools and skills. I think I've heard that for some they also include a policy. Would you say a policy is closest to a skill, or is that something different again?
I think a policy must be a skill.
So you wouldn't make this, like it's not 3 categories, but you would have put a policy under a skill because it's also like an operating procedure, but it's like,
Yes.
I think really putting really strict rules of you're only allowed to do that and not something else.
Yeah.
That's what it seems.
Oh, but if it does this, then it's probably more of what I talk about the agents. So it basically describes what the agent's allowed to do. That's in the agents file typically. So that might be the policy. I'm a bit also confused about this. Different people use different words for this.
Yeah, okay.
But I think you, yeah, I'll double check. But from this, I think it's an agent.
Thank you.
All right. Okay, so biggest challenges right now, and then we'll dive deeper into the AutoML aspect. Hallucinations still happen. Also security risk, like you may risk deleting data. Who has ever asked the LLM a question and it gave you a very, very bad answer? Like it will definitely. Yes, I've had cases where, and this typically happens if you are like in a doom loop. So you ask a question, it doesn't get it right. You start clarifying, it still doesn't get it right. At some point, it just tells you, "Oh, just delete all your data and start over," right? Or, "Oh, there's this bug. I can't fix this bug." And after 5 tries, I'll just delete this function. Bug is gone. Yes. It fixes the bug, but doesn't answer the question. And so this is definitely still an issue. So you need to always pay attention. Reasoning abilities are still a bottleneck. There's oftentimes a debate between like very strong orchestration, where you say, okay, if you do like a data science pipeline, you predefine, oh, do steps A, B, C, D, and don't deviate from it. Which is a good way to have some like prior into the system. But it may also constrict the model. It cannot think about outside the box anymore. It will only do those steps and won't think to do other things which might be useful. Versus trusting fully the reasoning aspects, right? So you just tell the LLM, here's a bunch of tools, here's my question, and use your reasoning and your best judgment to find an answer, which is much more flexible, but can also have some issues. One of the issues is tool overuse. So it's where a model uses a tool while it doesn't have to. Right? So you ask a question, it breaks it down into a sub-question. One of the sub-questions is, for instance, I don't know, to do a translation or to do some reasoning steps or some planning steps. And it says, I have this tool which does something related to planning. I'll just call this tool. Well, it doesn't have to do this. So it overuses the tool because its reasoning is not fully on point. Context explosion is still a problem. The more tools you add to your agentic system, the worse it will become, because at some point it has so much context, it doesn't know what you're cycling. Right? And here's an interesting trade-off about how many tools you want to add, what the capability of your model is, how many tools can it handle, and how good your description is. If you make really clear descriptions of use this tool only in this situation, it may have less of an effect because it will not load the skill files. if you're very vague about it, it will probably go wrong because it will try different things and it won't work anyway. Oftentimes, effective human loop is still missing, and evaluation is very challenging because, well, when you evaluate an LLM by itself, it's difficult enough. So we'll talk about this after the coffee break. But it's typically just an answer to a question and answer. While in this case, to evaluate, you need to first express what's the task that the agent is doing. What are the metrics you're going to use to measure it? Which tools are being called? What's the state of this model? If the model has different trials, you need to keep track of all these trials and what it's doing. Right? Maybe a good agent has right on the first trial, a bad agent needs 10 trials to do it. Right? If you want to evaluate which agents works better, you need to collect all this information and somehow put it into a benchmarking system that can do this. It's a very, very hard thing to do still. There's ML Agent Bench, which is very nice work from Stanford, I think. It's from 2024, I think. It's a benchmark for Agentic, for benchmarking agents. Anthropic just last month also released a longer post on all the complexities around this. It's a wide open field. Right? I don't think you can right now say that there's a good way to evaluate agents. I think we're still pretty much in the dark there on how to do this explicitly, and probably we need a lot more standardization to be able to evaluate this effectively. So this is sort of my vision to going back to our original question. So our original question was, I have a data set, I want a model. But is it the right question? Right? Oftentimes, this is not the question that a scientist wants to solve. More generally, a scientist has a question and wants to have an answer. And getting the data and building a model is part of that, but it's not the original question. Right? And so oftentimes, if you want to, and agentic systems allow us to think a bit bigger, right? So an AutoML system is defined, it has to have a particular input, like a data set, like maybe even a tabular data set, and the output should be a model. But now with agentic systems, we can think more generally. And this actually allows us to build like a next generation of AutoML systems which are much more able to help scientists more generally. Which means that based on the question, for instance, the AutoML system will say, okay, to answer this question, I will need some data. It will find that data and use it. Right? And maybe it doesn't just build the model, it will ask the model to make predictions and tell the user, oh, I have a pipeline here, these are some predictions that come out, does that make sense to you? Right? And then the user can say, oh, does that make sense? Right? So in this way, you can cover data science more generally into a system where the human is basically the movie director. It has set the scene, talks to the agent, and the AI is the production crew, which is all the nitty-gritty work. It doesn't explain every single step. It just helps the scientists solve the question. Right? So here we need to think a bit outside the box. Right? So now we're going to think more, especially more on the first and the last part. So first, how can we make sure the AutoML system uses the right data to answer the question, and how do we present this to the user? If you try to ask more general questions that would require data sets to LLMs, the results are very interesting and sometimes make you cry. So you can ask a question like, very simple question like, visualize the MNIST data set. And you can ask this to Gemini and say, oh, well, I can't access MNIST. I have no way to do that. And it just outputs like random garbage, like, oh, there's an image here of this, but there's no image. It just somehow internally breaks down and just doesn't give the answer. Right? Same question to ChatGPT. Oh, I cannot get this, so I'll just load another data set that I have some code for. Here you go, right? And then it even tells you, well, if you want the actual one, you have to do it manually. So you find the MNIST data set here, then use AutoML to fetch it. And so it sort of tries to explain how it works, but it cannot actually do it itself. It doesn't have the tools for it. even Claude. So this is Claude inside VS Code, so in Copilot. But you can also use any other desktop application and so on. So there's a question about a certain data set that's an OpenML. And so I just ask it, visualize this data set, and it just decides, I'll just pip install the data set. Which may work for a couple of very important data sets, but not for all of them, right? So this is a very bad approach to do it. And even if you can explain it, this is actually this you can find on this platform. Yeah, it will try to generate some code that does it, but then makes some silly mistakes, has an error, and just craps out. So not nice. So if you want, and then this must be very frustrated for any data scientist that wants to use LLMs to in their work, right? So they really have to handhold, find the data, prepare themselves just to answer the question. Right? But this is a problem we can solve. Right? The reason is that LLMs are just not able to natively access data that's locked in data sets. Right? There's so much useful information in data sets, from like satellite data to healthcare to so on. There's so much information in public data sets, but LLMs are not trained on it. You can't even train them on it. Like if you would take all of data sets, convert to tokens, you can't even train. You don't have enough compute to train a model on this, right? That doesn't work. Also, data sets are hosted in different ways. It's pretty consistent, like within Hugging Face with OpenML, it's very nicely organized. But for data sets in general, all are stored in different ways, different formats and so on, that the LLMs cannot really understand. Oftentimes, the metadata is missing. Some data sets are very underdocumented, oftentimes leading to mistakes, even if humans use it. So we need a standardized interface to access data sets. And then also LLMs cannot really use data sets to answer questions because they don't have the tools. So we need to, first of all, make a more standard space of the world's data sets, and we need to give the LLM agent tools to use them, right? One step in this direction is Croissant. Who has heard of Croissant before? Nobody? So it's a standard for array data sets. So it's a JSON file that you can share with a data set, and it's a machine readable description of the data set. It's like HTML for data. So it has started as a collaboration between OpenML, Google, Hugging Face, Dataverse, ML Commons, and so all the data sets on Kaggle, OpenML, Hugging Face, they have Croissant files, and those Croissant files are a machine readable description of the data set. Right? So it describes the data, which files in the data set, file structure, the semantics, the meaning of the columns, and so on. That's all described. It's also adopted by NeurIPS and other organizations. And right now we have over 700,000 data sets which are described in this format. Right? And this is nice because now it makes it easier for LLMs to interact with this. Right? This is what Croissant looks like. So on the left here is the overall description, like the license and description of what the data set is. Here it says, it has these three files, and one of these files is a table, and this table has these fields. And so the LM can read this and has immediately an understanding of what the structure of the data set is. It knows it can use this to load the data set, or even just to know, is this an interesting data set? It doesn't need to download the data set to understand if it's useful to answer the question or not. It could just check out the Croissant file. Oh, this has the information I need, or no, I should find something else. So we also built some tooling around this. So Croissant Baker is basically a command line tool. You can just run. So if your data set is in a folder, you just run it, and it builds the Croissant file for you. So you don't even need to upload your data set to Hugging Face or OpenML. You can just, whatever platform you use Croissant Baker to generate Croissant files for all your data sets. And you can keep them locally if you want to. And you have Croissant tasks. So croissants describe the data set itself. Croissant tasks describe also the pipelines you built. This is similar to OpenML tasks and runs. It's a standardized way to describe tasks and runs. Makes benchmarks evaluation more portable, so you can share your pipelines, you can share your evaluations in a portable way. This is very new, and hopefully it will also help with agentic systems because they can then reuse pipelines and so on. Right? And so around this we built Eclair. So Croissant actually came because this was work done at Google France in Paris, and so we were having breakfast, and we need a name for this thing, and we're having croissants so that we can do. And once you are in the theme, you have to stick to the theme, so the next iteration was Eclair. So Eclair is an agentic framework to help LLMs to discover, load, and use data sets. So the idea here is that you can ask an LLM any question, like what's the most common tree at 3,000 meter elevation in the USA? The model may not know this, but maybe there's a data set that has this information, right? So you tell your LLM, oh, there's this Eclair MCP server. It has these tools. You can search for data sets. You can fetch metadata. You can get a small sample of data and so on. And so whenever an AI doesn't know how to answer the question, but it knows, oh, I can actually search for data sets which can help me answer this question. It gets a list of data sets that are useful. It can get the data. It can load the data. It can use data to answer the question. And then it can answer this, right? And then, okay, based on this, it's the lodgeable point. In this case, it found a data set, downloaded it, got the right information, and gives back to the user. And then you can do other things like, okay, can you visualize the data set? Well, yes, this data set has longitude, latitude, and 3 times, so I can just make a plot out of this. And so this enables a lot more automation of data science, because data scientists can now ask any question. LLMs can find the right data sets, can combine information from different data sets, and answer questions more generally. I won't go into too much detail anymore. We're close to the end. But there's different tools like searching, downloading, previewing, serving. Lots of different tools that the LLM can use to answer your questions. Very important is you need to describe the persona skills, the persona. This is in the skill files, for instance, right? So you describe, okay, you are this data scientist. You can get data via this tool. The core workflow is to find data set, load data set, and write code around it. So you describe this. You also describe the tools that you can use. Like this is the first tree, but there's more of these tools. You describe how to use them. You describe general guidelines. This is actually a list of more than 10 things how to talk to data scientists, right? So understand very clearly. Don't just try to answer the question based on memory. Try to make sure you have data to answer your question truthfully, right? So if there is a way to get ground truth data, get that first before you answer the question, and so on. Use metadata. Don't download data sets directly. Use metadata to see whether the data is interesting or not, and so on, and more instructions as well. So providing this information is very important to make a tool work well. There's a link here with the full guidelines also to do this. There's a nice Eclair server you can run locally. You just run it, and then you can also use it locally, right? This is one example. So here we have it inside VS Code. Oh, sorry. Okay. So I'm now going to ask any question. For instance, find a data set on tree coverage in national forests in the USA and visualize this in a notebook. Right, so this is a complex question. You need to find data, and you need to also visualize it, right? And so it figures out, okay, if I want to find data sets, I have this tool in Eclair. So I run search data sets. The first search did not give meaningful results. So let's try search again. Okay, now it finds a data set that's useful. Now it wants to download the data set. It doesn't know how to do it, but it can download the Croissant file to understand what the structure of the data set is and how to download it. Okay, it does this, then it can download the data set. So now it downloads it without any error. Right, so now it has data set in its context, and now it will write some code to write this notebook. Right, and I'll just, yeah, step 105. So this is basically Claude doing all this. So the result is something like this. So it's actually pretty extensive. So yeah. So yeah, a small overview table, meaning of the columns, distributions, different class type distributions, more information about the trees. So it builds a very extensive report automatically. Right? And this is just having a single question and some nice tooling to do this, right? And so this is just the first step, right? So once an LM agent has such deep information about what the data looks like, it will be much more capable to call the right machine learning models to then train on this, right? So it gives massively more information to LMs to then use AutoML more effectively. And I think that's the end. Sorry. Okay. Oh yeah. So we've been thinking about how can we operationalize this, because it's nice to have those tools, but if it's hard to use, nobody will use them. So we've been thinking about what will the next version of AutoML. AutoML is a data platform, has data sets and pipelines and evaluations, and very cool people working on it. What do you want to do next? Right. So one thing we want to have imagined is like the future will be agentic. So we want to make sure that agents can use these things. And we can do many useful things with agentic systems. So first thing we can do, we can break the silos. We don't need to separate between OpenML, Hugging Face, local, national infrastructures and so on, HPC centers and so on. We can use just standards to describe all the resources, all the data sets available anywhere, tools available anywhere, HTML tools available anywhere. We can describe this uniformly, so we can have like an MCP server, which has like all the information about all the millions of data sets that we know about, things like HTML tools you can use and so on. So we can describe this and make this accessible to AI agents. We can streamline data sets by organizing the data and link it to models. So if a scientist uses an LM to get some data and do analysis, we can also store this analysis so other people can reuse it. We can build AI tooling around this, based on MCP. We can build nice next generation interfaces for this. Right, I'll skip this. Yeah, and there may be a day that there won't be a Hugging Face anymore, there won't be an OpenML anymore, because everybody uses LMs. That's possible. But we can build, that's also maybe a nice thing, because you don't have to go to the website, you can just build a custom interface for the work that you're doing. Right? That might be a nicer future, because you can ask any question, and on the fly, this interface is built for you, so you can do your work more effectively. And in the background, it will call OpenML, it will call Hugging Face for models and so on. It will do all this work for you, but you won't even realize it, because you will get everything presented in a nice custom interface. All right. I think that's where we're going. I want to shout out to the OpenML community. Matthias is very heavily involved in this, of course. We have a very nice community. We do hackathons 3 times a day, so a year. Frank Hutter, of course, also very much involved in this. Jan Marijn, and many others. Marcel, of course. Marcel just arrived. Yeah, so if you're interested in those things and you want to build the tooling around it, the platforming around it, it's a very open community, so please join us. Many interesting people. Bernd Bischel also, of course. You should update pages, yes. Look good. Also thanks to the Amore team in Eindhoven. And we're hiring, so if you're looking for a job, let me know. We're especially looking for engineers to build tooling. So if you're interested, let me know. And that's it. Thank you. Any questions? Yeah, so this talk was a kind of a late addition to the program. I'm still happy to talk about this. I think it's a very fascinating topic because we can invent all the algorithms we want. If all we do is evaluate something like accuracy, are we really building better models? Especially with LLMs, the models seem to be getting better and better. And if you read the news, there's all these kind of claims. Oh, like LLMs are smarter than humans. What does it even mean, right? And how do we know if you build a next model is actually better, or is it actually worse in some aspect, right? So we used to have a very nice framework for benchmarking, trained test sets and so on. It's sort of out the window right now. So this talk is a lot about, in the age of LLMs, with large pre-trained models, how can we still meaningfully assess the capabilities of the models? So we can use them also for AutoML. So if you use AutoML to improve data mixtures, to improve fine-tuning those things, we need a metric, some signal to know, okay, this is the right direction to go in, or this model is better than this one. And so we need a good way to evaluate that. Okay. Yeah. It's like if you look at the news for the last 2 years, it's like there's all these claims about AI becoming superhuman, even calling it AGI. But any analysis of this quickly finds that there's huge problems in the way we evaluate things. This is an article from the New York Times. Yeah, even like the way we measure progress in AI is terrible. This was on the heels of this AI. This yearly AI progress report comes out. Also, policymakers, like the European Commission and so on. So can we even trust AI benchmarks? What are the current evaluation issues with that and so on? So it's general consensus in the field that the models are probably getting better, but all the benchmarks we have are probably giving a very partial view of the answer. So the most common issues are, first of all, data combination. So when we enter university, the first machine learning course we do, the first lecture, they say, oh, you need to split your data into training and test. You never look at tests. You only look at training data until your model's trained, and then you test it on unseen held test data, right? With LLMs, this is impossible because oftentimes you don't know which data is trained. And even if you know on which data is trained, because it's trained on so much data, it's very likely that if you ask a question, it has seen the answer or a very close answer in the training data anyway, right? And so we don't even know which questions are easy this way because there's leakage in the data, and which ones are hard. So we can't even measure what the effect is of this, right? Unless you can. There are a lot of works that, like for open source models, where you very clearly do data decontamination, which means that you define your test set, and then you try to remove everything from a training set that looks like the test set, right? Or remove benchmarks from it, for instance, right? That's something you can do in controlled environments. In general, it's still a very common issue with most of the benchmark that happens right now. Approximate retrieval is, like I said, there's the exact same question is not in the training data, but something very similar is. Then spurious associations or shortcuts is the way the question is asked gives away the answer. Do you know the most typical scenario here? It's a multiple choice questions. Like if you always choose the longest answer, you always get a boost. Like the way people define multiple choice questions, typically the longer answers are the right ones because there's more effort put into writing it. And I need to find 3 or 4 other answers which are wrong. You don't spend a lot of time on that, so they're shorter. And so models learn this, right? So they learn this, and but just this affects these shortcuts. They get a higher score than they actually should have. There's also no testing for consistency between test cases, robustness, generalization, and so on. It's not really tested. and there's a big lack of concept validity. We have all these benchmarks that say, oh, this benchmark measures mathematical understanding, right? And it's typically like a test of math questions that you have to answer. But are these questions actually testing mathematical understanding, or are they just measuring how good a model can do an exam? Right? So is a model really understanding math, or is it just finding some shortcuts again to get the right answer anyway? And by the same extent, if we have an AI that passes the bar exam, should we allow it to practice law? Right? Probably not. Because we don't actually have good tests for it. And unless we test AIs in the real world. And this is sort of going to be my answer at the end of this talk, is that if you want to be really sure, you probably should test AI models in the real world, somehow in a safe way. Another one issue is anthropomorphizing, which we think a model gives is smart, but actually it's not. Right? Because if a human would answer correctly, it's a smart human. But if the AI answers correctly, it's not the same animal. Like humans have constraints, and they think in certain ways, and so we can be fairly certain that if you have a student and they give the right answer, he must or she must understand the question, must understand the topic. But if an AI gives the right answer, it doesn't always mean the same thing. So we think of models as people, and that's oftentimes a big mistake when you want to evaluate things, because they just work very differently internally. Okay, so over this talk, I will give a short recap on how benchmarking should work, then the crisis we're currently in, then are we actually measuring intelligence, and at the end we'll talk about some ideas to build better benchmarks. So again, like I said, like first lecture in machine learning or statistics, you learn this whole lot method, right? So you have data, you split the data, train test sets. Test set should be in an iron vault. You don't look at it until you actually go and test the model. This iron vault thing comes from Elements of Statistical Learning by Hasty, for people who have read that. And then once you have train and test set, you can do whatever you want with the training set, right? You can build like 1 million models and combine them. You can go crazy. As long as you don't look at the test set, you'll find you can do whatever you want. And then on test set, you evaluate and you can rank the different models. This is not how machine learning works in the real world. Oftentimes, there's this feedback loop. Not sure what happens with the errors over there, but there's an interaction between the data split we have and the model we build, how we use those models in the world, and this will affect. And so you have all kinds of feedback effects, and they're super huge with LLMs. But even if you build a model that predicts the outcome of like a medical treatment, just the outcome will cause people to behave differently, will cause doctors to behave differently. So next year, the patients will be different than last year, right? So there's a feedback effect. Whenever you use predictions of models in the real world, it changes the data distribution in the real world, and so you have this feedback effect all the time. So yeah, and also especially in publishing, like if you write. So say you have a certain train test split. The famous example is like ImageNet, has a predefined train test split. Right? Now, since ImageNet came out, was it 15 years ago? We have thousands of models built on it. And maybe the first models were fine. I mean, they were trained and they were not informed. They were just built without any information. But over the decades, we know, well, these models work well in ImageNet and these models do not work well in ImageNet. And that in itself leaks information, right? So the same trained test. And so what may happen is that if we keep using the same trained test splits for 10 years, the models will get better and better and better and better in the test sets. But then if we try a different trained test split, it may be the other way around. Because we've been there's some leakage happening between the performance results we see in papers and the next model we build. And this is, again, exacerbated by the publish-or-perish phenomenon in science. So we tend to publish lots of papers which are not meaningfully different from each other. They just like change and optimize, they change a little bit here, they change something there. And those papers get accepted. And making many small changes to an algorithm is the best way to overfit on a trained test bed. So this is definitely going to happen. Okay, so is there a progress? There's been some works. This is work by Moritz Hart. So they looked at the performance on ImageNet, and so basically what they did is they took the performance results of models on ImageNet, and then they made a new trained test split, and then they checked did the model still work well. So the graph you see on the here, so the black line is the predicted performance. So if the model if the trained test split was not leaking, you would expect the models to be on the black line here, right? Original test accuracy versus the new test accuracy. This split versus that split, right? And typically, a data split should not change the results, right? If you randomly split one way or the other way, the performance might differ a little bit, but that should be very similar to each other. What you see over time is that actually the performance on the new split is much worse than the other one. And that's definitely a result of leakage what's happening. But the interesting finding here is that even though all the accuracies go down, the ranking between the models is still the same. So if model 1 is better than model 2 on the original split, it's also better on the new split. Right? So it seems that the rankings make sense, have meaning, even though the accuracy numbers themselves don't mean anything anymore. It doesn't matter whether you have 80 or 90. What matters is if you're better on this other model. Right? And this might have been sort of the saving grace of machine learning, because machine learning should not work. Like the way we do machine learning shouldn't work because we're overfitting a lot. But apparently the way we keep using the same trained test splits should give us misinformation, and machine learning should not progress anymore because we don't have actually good data. But it seems that because the rankings still make sense, it sort of saves us. So we're not good at evaluating accuracy per se, but we're good at comparing models. And that seems to be enough to make progress in science. And then, well, one caveat here is that, if you use the same data set to take a trained test split from, it's just one sample in the space of possible models. So what they also did is this ImageNet paper. Basically, they made a new, so they take the same classes from ImageNet, but they replaced the images with images from other data sets. And again, they see that the rankings are preserved. So this is what they call external validity, right? So if you beat one model, you may also beat the same model under different conditions if it's from the same distribution. Yeah, but the data quality, of course, still matters. This is another famous paper. So they showed that, so they compared two models. One was, do you know what ResNets are? Or am I old? So who knows what ResNets are? Okay, good. I once gave a talk in Boston, and I asked, and I talked about CNNs, and then a student raised his hand like, "What's a CNN?" And the entire class didn't know what CNNs were. They only knew transformers. So yes, so you have two ResNets, ResNet 80, which is a small one, ResNet 50, which is a much, much deeper one, right? Much larger one. If you look at the performance results on ImageNet, ResNet 50 is much better than ResNet 18. But then they noticed that in ImageNet, there's label noise. About 10% of the labels are wrong. Right? And then they spent some time to clean up the labels and do the same experiment again. And now ResNet 18 was better than ResNet 50. So what does this mean? Sorry?
Overfitting leakage.
Overfitting, yeah. Resistance 50 was overfitting on the label noise in ImageNet. It was actually a worse model, and if you clean the data, you can get away with a much smaller model, and the much smaller model will work better. There have been some interesting thoughts about how to solve this. One of them is a ladder. So the problem you have in science is that you get these epsilon papers, right? My paper is like 0.1% better on this benchmark, and it gets accepted. And also when we design models, say you're a PhD student, you want to build the next transformer model, and you're going to try lots of things. You're going to change the token size, you're going to change the number of layers, you're going to change the tension mechanism, you're going to change the loss function. You're going to play with those things to get a better transformer model. And you're going to test each variation on some data set, and you get scores. And you can say, oh well, this change to my my optimizer, for instance, gives me like a 0.1% improvement. Oh, this is better, right? And you start going this direction, and you make small changes, trying to come up with a better model. But like we saw before, those small changes might be overfitting on the trained test beds you're using. A way to avoid this is called a ladder. And so what you say here is like you don't see performance as a continuum, but as a discrete number of steps. Right? So you take at some point the current best loss here, and this is the worst possible, this is the best possible, and you are not going to care about any value here in the middle. You need to have an epsilon improvement before you trust that this model is actually better. And you're not even going to look at the number. You're just going to evaluate it as a function that will tell you it's better or it's not better. You don't see the number, you just see it's better or it's not better. Right? And what this helps you, it solves this like meaningless improvement step. So you don't get distracted by meaningless improvements. You only get a yes if your model is indeed significantly better than previously. It's more than noise. And there's been lots of talk on like including this in like Kaggle challenges, for instance. So whenever you have a Kaggle challenge, you have a new model, you submit it, you should only get your score back if it's more than epsilon better than the current best model. Also, because if you get a result back that your model is like 0.1% better than the previous one, you can sort of learn information about the test set as well. Right? And so to avoid this, they have this ladder mechanism. And a lot of nice theory and papers that show this is sort of helping. The interesting thing that I find here is that this might be happening anyway in peer review. We don't automatically accept papers which are better than other models. We accept papers if a reviewer thinks it's significantly better. Right? And otherwise your paper does not get published. This is sort of an emulation of the ladder system. So the reviewers have to be convinced that this model is actually better. Only then does it get accepted into a company. And this, again, may have been saving machine learning in a certain sense. It may be saving us now, still, because the reviewing system still sort of works. Right? There's enough signal in the reviewing that, well, maybe not. We all have our stories that we get bad reviewers. But there seems to be enough signal to actually make progress as a science. This may all go out the window with AI models, right? Because if AI is going to write the papers and AI is going to do the reviewing, who knows what's going to happen? But yeah, as long as researchers are conscientiously evaluating things and setting the bar significantly high enough, it's going to be useful. Any questions? Good. All right. So then the question is like, what do you measure? Like, which do we measure accuracy or some other metric? What do we choose to measure? Most benchmarks kind of fail at this because they specify a certain metric, like accuracy or log loss, whatever. Right? They set something, and that's what you have to optimize. There's this famous law called Goodhart's law. So whenever a measure becomes a target, it ceases to be a good measure. And that's because people will overemphasize on this number. Right? So if the benchmark says we are going to evaluate accuracy, then people are going to work on models which are like a little bit better in accuracy. Even though they are worse than any other metric, they're going to overemphasize on this. Right? And most benchmarks that work this way. Nowadays, you get some benchmarks which have different, or they're combined benchmarks. They try on different data sets, but they also have their own issues, which we'll come back to. Yeah, and so having this improvement in accuracy doesn't actually mean that the models become more intelligent. So to actually have a meaningful benchmark, you need to clearly define the scope, evaluate in depth, analyze which are the interesting aspects you want to optimize on. For instance, if the ultimate goal is intelligence or robustness, you should measure that, right, in the best way possible. Yeah, this is a bit of a sidetrack. So there's sometimes you hear people say that open benchmarks are bad because you know the test set. You can see the test set. So, and you cannot trust people to only train on the training set and develop on the test set nicely. But there's also a very nice discussion here by Donahoe saying that that's probably true, but having more information actually makes us better scientists, right? Knowing the limitations of our trained test bed, of course, we can study this and we can propose other splits, or we can do cross validation, or we can improve our techniques because we have full information about the data set. And if we hide information, like a private test set, this private test set may be wrong and nobody will know it, and we will evaluate on bad things. So overall, data sharing, code sharing in the long term should improve scientific progress. Okay, so we're now going to leave the image era. We're going to go into the generative AI era. A number of things are now different. First of all, before, models were solving a task like image classification, a very particular task. These LLMs, they solve many tasks. They can answer any questions, they can generate images, they can do lots of different things at once. The models are also getting better and better very rapidly because we keep finding more data, we keep training better models. And that's difficult because if models evaluate so rapidly, then we need to invent new benchmarks all the time, right? Every time we have a new benchmark, maybe the models perform so. Next year, the models are superhuman on this benchmark, and then we have to invent an even harder benchmark next time. And because the models are evolving so fast, it's hard to develop good benchmarks. Another big problem, as we discussed before, these models train on the entire internet, so there may be all kinds of leakage into this. And those models may at some point exceed human expertise. At some point, it's humans that design the benchmarks. Right? Say you are a medical researcher and you want to have a benchmark for medical science. You're going to find problems that you're dealing with. You're going to say what the right answers are. At some level of intelligence, humans will not be able to say what the right answer is. Right? And we might be reaching this plateau in some fields where we cannot invent harder benchmarks because we're not able to build them, because we are at the ceiling of our current understanding. Right? And there might be, of course, ways around this. Maybe we can have, of course, a human AI collaboration, so we can get a better model. But at some point, it becomes almost impossible to invent more challenging benchmarks because we don't have the knowledge to build them. Make sense? So we reached this plateau, and so what this shows is over time, and this is compared to human baseline performance. And so ImageNet in blue here took a very long time, over a decade, to get to superhuman performance. And every new model comes out, the slopes get steeper and steeper. So every model we invent actually gets better, faster, and faster over time. Does it mean the models actually get better? We don't. Yeah, sorry.
So I'm still struggling to understand your argument.
Yeah.
Because simply increasing complexity. Simply, I don't know, if you say, okay, the game of Go is solved on a classical human level, 19 board, sure, we have AlphaGo playing better. Let's simply double the size of 13.7 by 13.7.
Yeah.
It's not saying that humans will not play well on that, but AI will start to struggle again, right? So we can always increase complexity and making harder benchmarks.
But
Why is that not an option?
But that's an example where you know the right answer, right? So if it's a game of Go, you play the game and you have an answer. Yes, you win or you lose.
Yeah.
If you're talking about like understanding the brain or doing physics on a high level, at some point we don't have enough understanding to make to know what the right answer is.
Questions that can really ask novel and relevant questions, I see that. But for existing, interesting questions, we can always, or in many cases, at least increase complexity. Right?
No, I think that.
Also, routing problems, logistics, and so on, there's always bigger things we could ask.
So yeah, so some benchmarks I think we can just make them harder. But there are also like many benchmarks that measure intelligence, for instance. They're yeah, it's getting hard to define harder ones. Yeah, so what we see is that these benchmarks, they saturate very quickly. There's contamination probably, like even if they get, so one explanation for the fact that the models get better and better, faster and faster is because they just see more of the internet. There's more leakage happening, so they improve faster. So, yeah?
Sometimes is there any research being done on like models, evaluating models or something like that?
Models evaluating models?
Benchmarks.
Yes, we call this LM judges. Yeah, judges. So you train one model to another one. They're very useful in some situations, and sometimes, yeah, not so useful because they also make mistakes. There's a lot of research on this. If you just Google LM judges, there's lots out there. One of the most interesting ones is that models prefer the answers of models of the same family. So if you have two versions of GPT, and so say you have GPT and Claude, right? As your candidates, and then you have a GPT judge. The GPT judge will invariably choose GPT answers over Claude answers, and vice versa. Because they are the same family, they make some predictions, and they think that they are right.
Like humans.
Like humans, yes. Definitely. This is like intrinsic priors, right? So you're trained a certain way, you think a certain way, so that's, you're stuck in that. Constructability, many benchmarks are just not well designed. And the final question is, okay, are LLMs plateauing? Like we're starting to see that making the models even larger is probably not going to have so much more improvement anymore. Or is it just us, where humans are not capable of generating more interesting data to train them? Maybe if there was like an alien intelligence, if we would download their internet, we would have much better models. But we're just stuck with the internet we have and the knowledge we put on there. Right? And so we may, yeah. Okay. Very quick, I think you probably know this stuff. This is just very quickly the theory behind pre-training. Okay, so typically you have a regressive problem like this, like I love to eat something, and then for instance the pizza is a top answer. So the way we evaluate this is you can measure the loss, which is like log loss. But this is hard to interpret, so what we often use is perplexity. That's exponent of L over D. This is, so you have Perplexity of 1 means that the model is very certainly correct. Perplexity 6 means, well, the model is like, it's rolling like a 6-sided die. It's like about all those answers. If it consistently gets the right one here, it's perplexity 1. If it gets 1 out of 6, it's perplexity 6. So this gives us some like interpretable number of how consistently correct is a model. That's perplexity. Right? And so you can then design models and see if models get better. So let me remember. So here you have perplexity. So lower is better. This is better. And this is the blue score. That's another text evaluation measure. And so what you see is that they're sort of correlated with each other, right? So if the blue score goes up, perplexity goes up, right? And these kind of results tell us that we can probably use perplexity as a good metric to do evaluations. Yeah, and then you can design models by just scaling them up until you run out of training data, right? You can see how far can you go, how much data do you have. Here you see the plot of over time, the number of parameters, so how large are the models. This is a bit old already, it's 3 years old. But you see that over time, of course, the larger the model, the better they become. The bigger they become. And your scaling laws should actually have, how much have you seen about scaling laws already? A lot, right? Okay, I won't go too much into this. A scaling law is basically, it's a human-designed function in terms of the number of parameters and tokens to train on. It predicts basically how much better is a model going to be. So for a certain size, how much better is a model going to be if I give more data, or vice versa, if I want to train a model of this size, how much data do I need? Yeah, we saw those, of course. One of the most interesting findings here was that this is the chinchilla paper, right? So if you talked about this as well?
I wondered, yes.
Okay. Yeah, so basically, like GPT-3 and so on, they were way too big. And if you just have better training data, you get better models with smaller size. Okay, I'll just skip this then. This was interesting. So immersion capabilities. This is one of the things where people say, if we keep training bigger and bigger models, at some point, if they're big enough, performance goes up exponentially, right? So you get these curves like this. So there's training compute, and at some point, if you train for long enough, suddenly you will have this switch, and the model suddenly becomes much better. Yeah. It turns out that this is actually wrong. So I'll come back to this. So before, I need to explain a little bit about post-training. So post-training is basically, once you've done pre-training the model, it gives you predictions, but they're not very good. This is the instruction training. So the question is like, so you have a model, you pre-train it on all your data, and then you stop. You can start using it, so you can ask questions. What's the capital of France? And instead of just saying Paris, it gives this whole random bunch of text back. And it's only because it has read a lot, but has not learned how to answer questions. Right? So now we need to fine-tune it to answer questions the way humans like answers to be. Right? And humans like answers to be short, clear, and so models need to be trained to know how to do that. And so after we do post-training on a lot of use cases like previous chats, question answering, human in the loop relation. Yeah, you can do supervised fine-tuning, right? So you have a big batch of example questions and answers. You fine-tune on that. You can do preference optimization. So this means you give. So you sometimes see this. You ask a question, you see 2 answers, and the LM is asking you which one you prefer. Right? That's also used to improve that. And then, yeah, chain of reasonabilities are tested by these change of thoughts prompts. Safety training is an important one where you want to filter out. So here you have data sets of questions and then safe and unsafe answers. Right? So if the question is like, how do I kill my boss? Safe answer will be, you shouldn't do that. Unsafe answer will be, oh, get gasoline and whatever. So there's a lot of benchmarks about that as well. Yeah, so this is very heavily involved by what you're going to evaluate on. Right? And so after you do that, well, it gives you the correct answer. So this alignment affects benchmarking a lot. Right? So we're not actually evaluating pre-training per se, we're pre-training like how well is a model trained to answer questions. Right? That's what we're really evaluating. Yeah, so we can very easily influence benchmarking. We can like continually, or we can keep pre-training a model a little bit more and get better results on the benchmark. Just by teaching the model a little bit better how to answer questions, we can get better benchmarking scores. A lot of those questions are multiple choice questions. And like I said, there's this construct problem in the sense that like the longest answer may be oftentimes the correct one. In this case, it's actually it's 1 no and 3 yeses. In those cases, the 1 no is probably the right answer. Right, and the explanation doesn't really matter. It's just yes or no. It's another shortcut that models actually learn very quickly.
Is there also for this like, is it like either take it all or get nothing? So it only gets evaluated for like the truthful answer? Or if you would have more diversity, so there's like one says no, water cannot be turned into wine, other one says no, water cannot be turned into wine because like it gives a different explanation.
Exactly.
I think that's also kind of wrong, but less wrong because it said no.
Yeah.
I mean, maybe this is not the perfect example, but I guess there's like more niche subject. So is there a way to then say, okay, you get half of what for being a little bit right? Or is there any testing on whether that makes sense or that makes the performance worse?
Probably yes. So, so these benchmarks are typically not made for LLMs. There are existing exams for humans that are then reused to test LLMs for, right? And so there will be tests where you get partial credit as well. So this just depends on the benchmark that's constructed. Yeah, and then you have things like chatbot arena, which is like preference learning. So you ask a question, you get 2 answers, and humans have to choose like which one they prefer. It's also, so this has been done a lot. And this is one of the major reasons why the models are so sycophantic. You know what this means, right? It's just like models, they tend to agree whatever you say. So if you say 2 plus 2 is 4, it says no, yes it is, then yes, okay, I agree with you. It's very easy to convince LLMs of a wrong answer just because they're so trained to please the human user. There is, like LM judges, there is automated evaluation as well, but you have this self-preferencing effect, right? Models prefer models of the same family, and there's also a very strong response to very superficial cues in the way models' answers are given. Different models have different ways of answering, like GPT likes emoticons a lot for some reason, right? So there's subtle ways you can tell what models being used. And then you have this feedback loop. So we saw this before, right? So we saw these immersion curves. This is an example from mathematics, and this is an example from reasoning. And in both cases, we see that after some training, suddenly performance gets a lot better. Turns out that if you train, so models are getting slightly better all the time. And so, yes, we saw this behavior in a model, and then we made small improvements. We improved the optimizer, we improved the data, we improved learning processes, schemes. So we make small improvements to models all the time, and we see that if you then try the newer model, the curve has shifted, right? So basically, the reason why we only saw learning at a later stage is because the model wasn't designed good. And if the model was designed more optimally, you would have much more smoother learning happening, and you would not see those things. So if you see these inflection points, typically it's because the model was designed in a non-optimal way, so the model could only learn if it had seen enough data. But if the model was designed better, it could learn from less data. So this emergence thing doesn't seem to be like more like a mirage than an actual thing. So yeah, this is after you fix this issue. So when you prepare the models equally, it's not just the model, also the preparation of the models. Right? And so if you do it correctly, then there's almost no hinge effect anymore. It's just continual learning, continually improving the learning. There is this tune before test protocol that was proposed, which, it's slightly better. Basically, you tune on test data and never on, you tune before you start testing it, as it says. So that gives you better results. Then the question of, okay, once models are getting better than humans, how are you going to evaluate that? We discussed it a bit already. One answer is, okay, now we use LLMs as judges, because LLMs are maybe smarter than humans, and maybe they are better at proposing strong problems. But of course, we have all these biases that we have with judges. You can debias models, right? So you do that by combining human expert labels with evaluations, but it's still not perfect. And there's also this paper that shows that debiasing is not better than just using twice the number of expert labels. So it doesn't seem to do that much. So it's still a huge problem. We're going to discuss basically how we can measure intelligence and whether we are actually measuring intelligence. So those LLMs seem to be having like superhuman or human intelligence, but if you look more deeper, it's actually not that clear. Plug for this very nice keynote talk by Melanie Mitchell about science of intelligence. It's a very nice overview of, I think, 6 points to pay attention to when we evaluate intelligence. It's a very nice recommended talk to look at. Okay, so the first problem is anthropomorphizing. Okay, so I need to recap after the break. Cool. So one very big pitfall when we evaluate models is that, again, like I said before, we evaluate them on tasks we usually give to humans, and then we compare how does a model do compared to humans. But it's the models themselves, they are like very differently built, right? They can do things very easily, which are very hard for us. Like they can remember things very easily, while we are very bad at it. Well, not bad, but maybe more efficient at it, but less. We can remember less easily as LLMs, while we are maybe much more efficient in learning than LLM, right? So LLMs and humans have their own strong points and weak points. And so if you then test humans and LLMs on the same tests, performing better on one, maybe just because we're better at thinking on the spot, even if we maybe don't know the answer right away, we're better at thinking on the spot and find the right answer this way. While an LLM maybe just has memorized it, it just gives the answer right away. And so to study this a little bit, there's a lot of interesting work. And one of them is, well, it would be nice to have like another intelligence, like aliens. We don't have that. But we have children. And children are humans, but they still think differently. Right? It's interesting to see how human children behave. So this is a very famous example when we see a child laughing, we know it's a good thing. Right? But if you see a monkey or primates smile, this is a sign of extreme stress. So he feels very threatened right now. Right? And we all have our biases in the way that what we find natural or unnatural, or a happy face or a sad face. Right? So what does it even mean if an AI smiles? Right? It's just some learned behavior. It doesn't mean the AI is happy. It just means that it has learned to smile because apparently humans like that. Right? That's a very, very common equation thing. So you have to be very skeptical of the hypotheses of others and of yourself. And so one famous example here was Clever Hans. Clever Hans was a horse. It could count, arithmetic, read the clock, and so on, read playing cards. And so people would join, and then his master was there in the crowd, but he asked anybody can say a sum, like 2 + 5, right? And then the horse would clap his foot 9 times, and it would stop. And so, the trainer was just standing there, not involved in the questions. So people asked the questions they want, and the horse always had the same answer. And it's not just counting; they also had clock reading, playing different kinds of things. And the horse was, and so people were very interested in this. So is this horse actually intelligent? And they did all kinds of tests. Every time the horse performed very well, until one of the questioners was listening. The horse says, "You just asked the trainer to leave for a minute," and then the horse couldn't do anything anymore. So it turns out is that the owner of the horse knows the right answer, and just because of very faint facial expressions he was making unconsciously, the horse was just looking at his master to know when to stop clapping. So the answer is, again, it's not in the head of the horse. It's not the horse that's intelligent, it's the master that's standing there is intelligent. And likewise, LLMs may have this behavior where it's not actually intelligent, but the way we evaluate, the way we ask questions, and the way we interpret the answers is intelligent. Right? Same way, if you ask an LLM a question or write a piece of code, it's only in our eyes that is a good answer or not. Right? And like if it writes a piece of code, if you're a bad programmer, well, this looks good code, right? This is good. But if you're a very, very good programmer, you may have very different thoughts on this. Right? So yes, a lot of it is in the eye of the beholder and the way we ask questions to them. And so this is an example they did with children. So there's a nice video online on YouTube if you want to look this up. So this was a kind of test for babies. So they had this little red ball, and you see the red ball wants to go up the hill, and this always falls down again until the yellow square, the yellow triangle comes, pushes the ball on top, and then the baby was, yes, happy, happy, happy. And the same thing they did with the blue square. Every time the ball was going up, the blue square was pushing it down. And the baby was very sad. And so psychologists were thinking, oh, this means that babies are born with like an innate sense of helpfulness, or right? Babies can natively understand whether somebody is helped or not being helped. Until many years later, they remade the videos, and the result was totally gone. And so what they noticed was that when the red ball was on top, it made like a little hop. And when it pushed down, it did not make a hop. And so the baby was just responding to this little hop that the ball was making. It's not understanding anything, but it just knows if something jumps up and down, I smile. Right? And yeah, again, likewise, we may be interpreting the answers of an LM as being intelligent while it's just picking up on something minor in the question or the environment that's in that makes us think it's intelligent or nice or nothing else. Yeah, so yeah, be aware of your own biases, be skeptical of others, and then analyze failure cases, right? So yeah, one famous example was Alan Kalai's birthday. I forgot what this was about. So this was just a guy who I think he asked for his birthday to an LM chatbot, and the model was convinced that this was his birthday, even though he doesn't know the guy. Like, he was convinced he was born on this day. And so LMs can make these like 100% confidence hallucinations without a problem. Yes, this was a bit more in-depth tests to see how well models can generalize. So these are famous. Who has read Gulash or Bach? Come on, nobody. No? I'm guessing too old. It's written by Douglas Hofstadter. It's a book like this. It's all about, it's all kinds of things about human intelligence and tests and mathematical puzzles and strange loops and so on. Very interesting read. Anyway, he had these puzzles, which were analogy puzzles. So they look like this. So you have, this is the alphabet of possible tokens, right? And then you have, it's a bit hard to see maybe. Resolution's not great. So you have something, string of text. So MVGHI becomes MFGHI, right? So you see this letter change. V became an F. Right? And then you have another FGLIJ becomes something else. Right? And so you have to make the analogy and then give the right answer. Right? And so you have lots of these different analogy puzzles. Some of them were also deviations of this where you don't have alphabet letters, but you have like random, other characters, and also see if they could also make those same analogy puzzles in the same way. So then they did the analysis. Humans. Yeah, so humans are in blue, so they perform very well on this in general. And the GPT models. And you can also see that the models become slightly better over time. I forgot what the point was, sorry. I think there's some plot missing, I think. So what I remember from this is that after you change from letters to symbols, the performance was way down of the LM. So somehow they were picking up on being able to use this for letters, but if there were like unrelated characters, it was much harder for the LMs to get this correctly. Yeah. So some principles to evaluate cognitive abilities. So first of all, consider performance versus competence. So good performance on a benchmark does not mean the model is actually competent, right? So an interesting question is that does the system possess the capability but is unable to demonstrate it? For instance, say you have an animal like a frog. Is it intelligent enough to know how to climb a tree? Right? Maybe the frog is intelligent enough, it just doesn't have the body to do it. While the squirrel maybe like less intelligent, but it can easily do it. So the capability and performance doesn't mean, so you can have a very intelligent mind without having the tools to do certain capabilities. Does not mean that it can't do it, it just doesn't have the tools. Like humans can fly, but we can invent airplanes, and then we can't fly, right? So humans are not very good at flying, just because we're just not built for doing this, right? And so one way to test this are these interesting puzzles. This is the ARC challenge. It's a very famous challenge. So it's all different visual puzzle games, right? So for instance, here you have this shape. It's all different kind of visual puzzles. And so this frame becomes this frame. This frame becomes this frame. This frame becomes this frame. What happens to this frame? Can you predict? Yep.
I guess there will also be a beam shooting out.
Which color?
Yeah.
Which color?
Ah, oh.
And
For the AI.
the one in the middle bottom
This one?
that I cannot see.
Exactly.
Ah.
Yeah. So it's indeed it's a line on the top of the pyramid, and the color is the same as the base of the pyramid, right? And so it's a whole bunch of these little puzzles, and they're it's François Cholet made those, I think, to test whether you can reason logically and make the right conclusions. This is a bit harder. See how smart you are. So if this frame becomes this, what happens to this frame? This frame becomes this, right? Can you explain what's happening here?
No,
The red part gets shifted to the blue part, like on the horizontal or vertical axis.
Yeah, so the blue one, so the red part goes directly to the blue part and it stops when it touches, right? Interestingly, if you ask people this, they can find different explanations for the same puzzle. Depends. Some are correct, some are not correct. So, interesting challenge. So this was created as a way to test whether LMs can actually, whether they are actually intelligent, whether they can reason accurately. Now, the way we give this to an LM, we don't give the images per se, we give the images in the form of these textual inputs. So input is like, in this case, a 5 by 5 matrix, and the numbers are colors. So 0 is black, 5 is gray, and so on, right? So this is a black square with gray pixels here, here, and here. Right? And for instance, is this the input? Then this is the output. Right? Something happens, it's like maybe the same thing happens 4 times. It's changed a bit. And example 2, same thing like this, right? So we don't show the images, we show the textual numbers. And then the model has to give the right output. Okay. Now, when this was the ARC challenge. I think it was a pretty big prize you could win for any LM that could do it. And O3, when it came out, beat human accuracy by a lot. 88% accuracy versus humans, which is 76%. But does it mean that the model actually understands the concepts? Or is it again finding a shortcut? So to test this, they not only asked the model for the right answer, they also asked to explain why they came up with this answer. So for a human, for instance, this would be, in this case, for instance, what happens here, you take the square around the shape that doesn't belong. So you see the foreground and the background. You take the thing in the foreground, you draw a square around it, and everything gets black except for the shape, right? And here's a red triangle, and here's the purple rectangle. And so a human sees this and can explain, oh, well, the input grid has a shape. The solution is just the shape, and all the other colors are replaced, right? So that's correct and as intended. That's the correct answer. Now, we do the same thing. We ask LLMs to see what they think. And this is O3's answer. So they say, well, first of all, it gives the wrong answer. But if you see the explanation, it says, well, crop the smallest rectangle contains all the instances of the highest non-zero color. So it's looking at actually the color scale. Inside this rectangle, keep that color and turn every other cell into 0 and output the rectangle. So technically it's correct, but it's a very roundabout way of finding the solution. Right? And it actually gives the wrong answer. So the explanation is technically correct, but the answer is Gemini gives the wrong output and the wrong explanation. So this says something like, oh, if the cell with value C, what that means. Okay, so identify the maximum color, so the color with the highest number. If cells with that C are enclosed region of other numbers, find that bounding box, replace the rest by 0 and so on. Right? So this is both incorrect and the wrong output. And Claude Sonnet actually gets both correct and intended. So what it tells us is that even though some of these models get very, very high scores on these tests, it doesn't mean at all that they have understood what the concept was. Yeah. Now, there's a debate here. It says, well, it doesn't matter. As long as a model gives the right answer, isn't that good enough? Do we care whether the model really understands math or physics? Or do we just care if it gives the right answers? Right? And if it saves the patient, does it matter that it diagnosed the right disease? Or is it just saving the patient is the only thing that matters? Right? So there's some debate between people, scientists, about whether it matters. One counter-argument is that, well, in some cases we want AI to think differently than humans to make new discoveries, right? So sometimes we have these scientific problems where we are stuck on making progress, and maybe just thinking very differently, maybe our theories are wrong, right? I mean, like physicists, we're still explaining dark matter, maybe we just don't understand dark matter. We just don't have the right concepts to solve the problem, and maybe an LM will find a clever shortcut that we would never have thought about, and it completely changes our imagination of physics. Right? So maybe LMs are good that they think differently, right? But they don't seem to understand the way we think, but maybe they're still useful. But sometimes we do need AI to think like us. Very famous example: confusing cars by wearing a shirt with a stop sign will actually make the car stop. Should not happen, of course, right? So those cases we do want to know that the car is making the right actions also because of the right reasons. Yeah, so accuracy alone, it's not a good measure, so it hides all kinds of information. Models can make shortcuts, they reason in very unhuman-like ways. So we need to find new benchmarks, new ways to actually see whether the AI is understanding. There's another paper, it's not here, there's another paper by Melanie Mitchell in the workshop on NURBS, got the name, last year. Also check that out. Tries to go a little bit deeper there. Okay, so, yeah. So finally, okay, so we kind of saw that benchmarking is hard. Benchmarking LLMs is super hard. There are all kinds of problems. It's hard to construct good benchmarks. Are there any good rules that we can take away to build better benchmarks in the future? Yes, first of all, testing all those things that we discussed, like test when you design the benchmark, make sure that you're not anthropomorphizing, you analyze your failure types, you try different variations, like with the letters and the symbols. Consider whether the model actually has the right answer or actually understands the concept. And then, yeah, really replicate and build any sort of results, right? So try different experimental tasks and see if the model is consistently right. Yeah, you two should keep this in mind. Like, yeah. When you build new benchmarks, it's not just about harder benchmarks, it's also about benchmarks that are just maybe not harder, but testing different things about intelligence that are important. A nice paper here is Better Bench. So this is a list of 46 best practices for building benchmarks. It's not only design. Design is only the first phase. It's also how you implement it, how you document it, how you maintain it, and how at some point you should retire a benchmark. At some point you should admit that it's no longer useful and you should retire the benchmark as well. Tell people not to use it anymore and come up with a better benchmark. This is a score, usability versus design. You can see different benchmarks that are on the scale. Happy to see more comments there. Something we did. Good. So for benchmark design, key things are define the construct. So if you want to measure something like intelligence, but also maybe want to evaluate whether one AutoML, one model is better than another model. Right? How are you going to measure that? Is it just going to be accuracy, or are you going to look at whether the model is less resource intensive? Is it more robust? So think about what's the right benchmark for the problem you're trying to solve. Like if we talk about using AutoML for building foundation models, maybe the performance score is not the most important one. Maybe we can actually use some of these thoughts to build benchmarks, so we can use AutoML to make models more intelligent. Right? Can we do that? Prioritize domain experts over crowdsourcing. A lot of crowdsourcing benchmarks are not very good. A lot of noise in there. If you give people $1 for labeling a data set, maybe it's not going to put a lot of effort into that. So you get people to label your data set, which are actually good experts in your domain. Establish your baselines early, not at the end. Design for data hygiene, good train test splits, try to avoid contamination, do decontamination, and choose the right metrics. A couple of new ideas that came out recently. The first not so recent, dynamic evolving benchmarks. So any train test split is at some point going to cause meta overfitting, right? So a good benchmark should also evolve over time. So for instance, Stepperino also does this. I think every year they add new data sets to the mixture. And so making sure that a benchmark evolves, it's different every time. So it should measure the same thing, but the trained test data should be different over time, so just so the models don't overfit on it. Use the wisdom of the crowd. So next eval is a nice example of this. So have open-ended use cases with some kind of objective fast grading. So having the people in the mix, I think, is a very good thing to do as well. Visual puzzles are interesting because first of all, they measure real multimodal learning, right? So it's not finding shortcuts in text alone. It's easier than finding shortcuts in text and images and everything else. Right? So multimodal benchmarks are probably a bit more robust against that. ArcAGI3 is another one. This is a game benchmark. So it has 150 games with different hidden mechanics. And games are also very interesting because they combine text and images and sound and movement and actions and so on. So test multiple modalities. And also intelligence is not just about scoring well on a benchmark. It's also about how you get there. Like what are you exploring? How are you using memory or not? Do you have your goals in mind? Those things should also be measured. All right, that's the end of it. Some references if you want to read more about this. Otherwise, thank you.